Lecture 12, Gases. Objectives. Learn about atmospheric pressure and how barometers work. Learn the various units of pressure. Learn the law connecting gas pressure and volume. Do calculations involving this law. Learn about absolute zero. Learn about the relationship between the volume and temperature of a sample of a gas. Constant moles and pressure, and do calculations involving this law. Understand the law connecting sample volume and moles of gas at constant temperature and pressure, and do calculations involving this law. Understand the ideal gas law and use it in calculations. Understand the relationship between the partial and total pressures of a gas mixture and use it in calculations. Understand the relationship between laws and models, theories. Understand the fundamental postulates of the kinetic molecular theory. Understand the term temperature. Learn how the kinetic molecular theory explains the gas laws. Understand the molar volume of an ideal gas. Learn the definition of STP. Use this concept in the ideal gas equation. 1. Atmospheric pressure and barometers. Atmospheric pressure is the force exerted by air molecules colliding with surfaces. At sea level, air molecules form a tall column of gas. The weight of this column creates pressure. Barometer. A barometer measures atmospheric pressure. A mercury barometer consists of a tube filled with mercury, inverted into a mercury reservoir. Atmospheric pressure pushes mercury up the tube. At sea level, the mercury column is 760 millimeters high. 2. Units of pressure. Common units include unit, relationship, atmosphere, ATM, standard reference, mmHg or torr. 760 millimeters of mercury equals 1 ATM. Pascal PA. SI unit, kilopascal, kPa. 101.325 kilopascals equals 1 ATM. Key equivalence.
ATM igual a 760 milímetros, Hg igual a...
1 atmosphere is equal to 760 millimeters of mercury, that is equal to 760 torr, and is equal to 101.325 kilopascal. In the first law, the Boyle's law, when the temperature and the moles are constant, the pressure is inversely proportional to volume. When the pressure increases, the volume decreases. The mathematical form is this one. P1 V1 is equal to P2 V2. Decrease in volume increases pressure, and increase in volumes decreases pressure. Example, a gas occupies 2 liters at 1 atmosphere. What is the pressure at 1 liter? Then what you do, you are looking for the pressure, then P1 B1 divided P B2 is equal to 2 atmosphere. Let's see what is the absolute zero.
Absolute zero. Absolute zero is the temperature at which gas particles theoretically have zero kinetic energy, defined as 0 K, equivalent to minus 273.15 degrees Celsius. At absolute zero, particle motion stops, theoretical limit. Volume extrapolates to 0. 5. Volume-to-temperature relationship, Charles's law. When pressure and moles are constant.
Okay, when pressure and moles are constant, you can see that the volume is directly proportional to temperature, and this is a mathematical form of the law. Remember that the temperature must be always in Kelvin. Example, a gas has a volume of 3 liters at 300 Kelvin. What is the volume at 600 Kelvin? Then you multiply the volume by the temperature 2 and the temperature 1 in Kelvin, and the answer is 6 liters. Now, volume moles relationship. This is the Avogadro's law. The volume is directly proportional to the number of moles represented by N, and this is a mathematical expression. So, if you double the number of moles, what happened to the volume? Also is double. The ideal gas law is a combination of all the laws. And the expression, the mathematical expression is pressure times volume is equal to the number of moles times the R constant times T. The R constant is the gas constant. That generally is this value, 0.08206 liter per atmosphere, moles inverse, Kelvin inverse. For example, if what is the volume of 1 mole of gas at 1 atmosphere at 273 Kelvin? Then you change the value here in the formula and you find out that is 22.4 liter. This number is very, very important because this is the volume that occupies any gas at STP. What is the meaning of STP? Well, standard pressure, 1 atmosphere, and standard temperature, STP. Then at STP, 1 atmosphere and 273 Kelvin, any gas occupies 22.4 liter. The total pressure, or the Dalton's law, is the sum of the partial pressures. How you get the partial pressure? Well, the partial pressure is the total times the fraction of the gas in a mixture of gases. All right, let's see the different laws and model theories.
Laws versus models, theories. Laws describe what happens, Boyle, Charles. Models/theories explain why it happens, kinetic molecular theory. 10. Kinetic molecular theory, KMT fundamental postulates. Gas particles are tiny compared to the container. Particles are in constant random motion. Collisions are elastic. An elastic collision is one in which no kinetic energy is lost to heat, sound, or deformation. The total kinetic energy of the colliding particles before the collision equals the total kinetic energy after the collision. Momentum is also conserved. No attractive or repulsive forces between particles. Average kinetic energy depends only on temperature. 11. Temperature, microscopic meaning. Temperature is a measure of the average kinetic energy of gas particles. Higher temperature, faster particles. Lower temperature, slower particles. 12. How KMT explains gas laws. Law. KMT explanation. Boyle's. Smaller volume, more collisions, higher pressure. Charles's. Higher temperature, faster particles, larger volume. Dalton's. Each gas collides independently. 13. Molar volume of an ideal gas. At STP.
Un mol gas igual a 22 d'abril L.
Okay, one at STP, standard temperature and pressure. Remember, the pressure is 273 Kelvin and the pressure is 1 atmosphere. This is what we call STP. A gas occupies a volume of 22.4 liters. This is a very important constant. Don't forget about this. This is the temperature and this is the pressure for a standard STP, standard temperature and pressure. Using STP and the ideal gas law, what you're going to find? Look at this.
Quick mole of volume conversions. Simplified gas calculations. Comparison between different gases. Summary. Gas laws describe measurable relationships. The ideal gas law unifies them. The kinetic molecular theory explains them at the particle level. Here are 5 conceptually tricky gas law questions, designed to make students think, not just plug numbers. Each targets a common misconception in this unit. I include the answer plus brief explanation. 1. Boyle's law, hidden variable trap. A sealed syringe contains a gas at constant temperature. The volume is cut in half. A student claims that pressure doubles only when gas particles move faster. Is the student correct? Explain. Answer, key crossmark incorrect. The pressure doubles because particles collide with the container walls more frequently, not because they move faster. Since temperature is constant, the average kinetic energy and speed does not change. 2. Absolute zero, conceptual limit. Extrapolating Charles's law suggests that the volume of a gas becomes zero at 0 K. Does this mean gases actually reach zero volume at absolute zero? Answer, key crossmark no. Absolute zero is a theoretical limit. Real gases condense into liquids or solids before reaching 0 K. The law works only within a specific temperature range. 3. Dalton's law, partial pressure misconception. A container holds helium and neon at the same temperature. There are twice as many moles of neon as helium. Which gas exerts the greater partial pressure, and why? Answer, key neon exerts the greater partial pressure. Partial pressure depends on the number of moles, not molar mass. At equal temperature and volume, more moles, more collisions, higher pressure. 4. Ideal gas law, our value trap. A student uses the ideal gas law with pressure in kPa, volume in liters, temperature in Kelvin, and mascula are equal to 0.08206. The numerical answer seems reasonable. Is the calculation valid? Answer, key crossmark invalid. The value of parenthesis de apertura mascula are parenthesis de Sierra equal to 0.08206. Our EQUI, our ES pressure in ATM, not kPa. Using inconsistent units gives a numerically plausible but physically incorrect result. 5. Kinetic molecular theory, speed versus mass. At the same temperature, which gas has the higher average molecular speed, hydrogen, H2, or oxygen, O2? Answer, key hydrogen, H2. At the same temperature, all gases have the same average kinetic energy, but lighter molecules move faster than heavier ones.
Okay, this is all for this lecture. Stop the video, go back and try to see all these questions, because these questions will clarify the way I will ask you during the test and during the quizzes. See you in the next video.